All right, so kind of welcome to part 5 of chapter 5. So this is the last little bit I want to talk about for chapter 5. There were some kind of important topics that didn't really fit in well in other places in this lecture, but they're important things to understand about molecules, so I want to make sure you hear them straight from me. In this video, we're going to talk just a little bit about how we can learn about monatomic and diatomic molecules, how we can use the periodic table, our bestie, to identify them. We're also going to talk a little bit about two different kinds of models we use to represent molecules called ball and stick models and space filling models. We'll talk a little bit about each, what you can learn from them, why you might want to use one or the other in different situations. And then finally, in a separate video, we'll talk a little bit about formula mass. Again, these are all really important things. They just kind of didn't fit into the theme of the story I was telling for this chapter. Buckle up. Let's talk about some diatomic molecules and some models. Elements really, when we're looking at the periodic table, can exist in one of two ways, okay? So they might be just individual atoms hanging out, how we expect elements to be, kind of what you might picture in your head, just individual little dots of something hanging out. We would call this like the elemental form. However, that elemental form of specific atoms isn't always just one atom hanging out. Sometimes we have what we call diatomic molecules or diatomic elements, or you might just hear me call them the diatomics, okay? So what I'm trying to say is that they actually exist as a molecular compound in the end. So instead of just one hydrogen atom hanging out, when we're talking about elemental hydrogen, when you point at the periodic table and you say hydrogen, you're actually talking about H2, okay? So diatomic, di meaning two, atomic meaning atoms. So we have two atoms here. So hydrogen is a diatomic. So if we're talking about that elemental form, that kind of pure form of just hydrogen as it exists, we're actually talking about H2. So there are many different diatomic molecules, diatomic elements that exist on the periodic table, and this is your list of those elements on the periodic table. So there are a few different ways you might remember this. There are a few different things you might use as a trick to kind of jog your brain, but I do kind of want you to get to know the diatomics on their own without any resources, okay? If you're talking about an elemental diatomic molecule, like we're just talking about oxygen, so when we say we're breathing oxygen in and out, we're actually breathing in and out O2, right? So you should always make sure that you're reporting something as that diatomic in its elemental form if it is a diatomic element, okay? So these are your diatomics. Get to know them, love them. They're mostly halogens with a few exceptions. And the way I tend to remember them is through this funny little mnemonic down here called, I'd say that Brinkelhoff, okay? Brinkelhoff. So Br for bromine, I for iodine, N for nitrogen, Cl for chlorine, H for hydrogen, O for oxygen, F for fluorine. So in my head, I'm always like, Brinkelhoff. It's a Brinkelhoff. You know what I mean? I'm just meaning it's a diatomic molecule. But there are other ways to remember this as well. And again, this is important so you're properly talking about the elemental form of these molecules, the actual proper molecular elemental form of these compounds. So some people also like to remember it using the periodic table. So there are 7 diatomic elements, and they make mostly a little 7 on the periodic table. So that corner with fluorine, you have oxygen and nitrogen, then you have the corner with fluorine, then you have chlorine, bromine, iodine, and of course hydrogen's always the exception, so duh, hydrogen, right? So again, these are the diatomic elements, so they exist as diatomic molecules in their elemental forms, and again, you should get to know this because this is also going to affect things when we're starting to talk about chemical reactions and what we can learn from a chemical reaction in the end. Kind of start to stick these guys in your brain, have them ready to pull out of your back pocket, and you know exactly which ones those diatomic elements are. Again, you can use Brinkelhoff like I do to remember this, or you can kind of remember them as that number 7. There are 7 of them, as that number 7 and hydrogen on the periodic table. So that aside, the other main topic of this video is to talk a little bit about some molecular models. So anytime we're talking about a model, it's some sort of conceptual representation of it. So like literally, we're not going to put individual molecules sitting there on our paper, right? Like we're not IBM, we're not how they drew their logo in xenon atoms. We're not IBM, okay? We are chemistry students learning about chemistry, and when chemists are doing this in real life too, we're not separating out individual molecules doing this. So if I want to point out a specific feature of a molecule, I can't just hand you one water molecule and you would be able to look at it, see it, do something with it, right? We need like that electron microscope we talked about before. So we use a model to represent these things instead. So we're going to look at 3 types of models for those chemical formulas for now, and we're going to add some more to our toolbox later on as the semester goes on. So chemical formulas. Those are actually a model. I'm not putting 1 carbon and 4 hydrogens on my piece of paper. That chemical symbol with those subscripts gives a representation of what an atom or what a molecule might look like and tells us about the kinds of atoms within that molecule. It's a model of a molecule. So what's good about this is it's compact, it's easy to write, it's in your face, and you can see exactly that ratio of types of atoms together. But unfortunately, in most cases, it doesn't really tell us anything about the structure. You got to kind of do a lot of legwork to figure out the structure, which we'll learn about later. But you got to do all that legwork to figure out the structure. So if you want structural information, a molecular formula is not the way to go in the end. But it's really good if you need something fast, compact, and very evident about what kinds of atoms and how many of each atom you're working with. We also might see a ball and stick model. That would be this one right here on your screen. So this is a ball and stick model. So each atom is represented as a circular ball, and it's connected to other atoms through a stick, which represents a chemical bond, okay? So this is like that chemical bond, that covalent bond that you find in a molecular compound. That's what the stick in a ball and stick model represents. So that might be that I take out my molecular modeling kit and I build you a molecule 3D real life with little fake atoms and connectors. Or it might be a picture of what you see here on your screen. So it gives us really good information about the structure, so we can very easily see how those atoms are hooked together. And it also gives us information about the number and type of atoms too. Because in a ball and stick model, we're always going to have different colors that represent different atoms. And you can find kind of a little translation chart here of that, of what those atoms are typically represented as. So hydrogen's always, always, always white. Carbon is always black, and oxygen is always red in this case. Sometimes you can find a little bit of variation in the others, but I promise you, any modeling kit you pick up, or anytime you kind of research these online, or you want to look at a picture of a molecule, you'll always find that those 3 are always assigned the same colors. So again, this gives us good information about structure. It gives us good information about the number and type of atoms that are hooked together. But it doesn't really give us a realistic picture of what atoms look like, or molecules look like. So, spoiler alert, molecules aren't actually kind of separated by a line that is a chemical bond, okay? They're actually, again, mostly that empty space, and they might have some overlap where they're sharing some space with another atom. So when we're putting molecules together, that chemical bond is actually really kind of that overlap of their electron clouds, where they're sharing some electrons in that electron cloud. So to do this and to kind of show off the feature of what a molecule might look like with those atoms fully at full force, full scale, is what we would call the space filling model. So we have the space filling model down here. So this is the molecular formula, the ball and stick model, and the space filling model, all for CH4. They're all of the same compound here. So in the space filling model, each atom is represented as a large sphere, and where they overlap represents a chemical bond. So here you can see where that white sphere is overlapping the black sphere. That's representing a chemical bond between a carbon and a hydrogen, just like what we see here as that line in the ball and stick model. It's giving us a good picture of what this molecule would look like in a 3D space, and it's giving us great information about the types of atoms and where they're located. And again, it's more realistic because those electron clouds are huge compared to that teeny tiny nucleus. And so and again, really in that chemical bond, it's how they're overlapping that create those chemical bonds. But the downfall here is it's kind of hard to see the atoms and how they're connected, right? So if you have a really long carbon chain where you have carbon, 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 you have lots of overlapping black spheres, which make it kind of really hard to count and tell how many carbons you have. CH4 here is relatively easy, but if we had like C2H10 or, C2H6 or C4H10, that butane we were talking about before, it's so much harder to actually see that there are 4 carbon atoms in the center building the chain of that molecule because they're black spheres that kind of overlap. It's hard to see. It is what it is. It's again really, really good because it's kind of the most accurate model we can picture in our head, but it kind of fails at telling us all the time the number and type of each atom. So there might be, again, different situations where we want to use these, right? So if I just want to tell you about a molecule and I want to talk to you about the chemical formula, the molecular formula is going to be the way that I do that, right? I'm going to write down those chemical symbols with the proper subscripts. If I want to kind of show you the connections and the number of types of atoms, I might choose the ball and stick model because that's going to be really evident to you what types of atoms you have, the number of type of each atom, and how they're connected to each other is very apparent. And again, we use molecular modeling kits with that ball and stick model all the time. However, if I want you to have a really realistic 3D image in your brain of what a molecule looks like, I might go for the space filling model in that case. Because again, that's that most kind of 3D space, what they kind of look like in real life. If we were able to kind of color atoms and have these different things. Again, this is kind of that 3D picture you can put in your brain of what it would look like. So each one has their advantages, each one has their disadvantages, and really what I want you to take away from this is kind of how to read these different things. So in the very first video, we talked specifically about chemical formulas, and here I just kind of wanted to point out the advantages, disadvantages here of ball and stick models and space filling models. And I hope that if I show them to you later on, you'll have a better idea of what molecule I'm talking about based upon having seen these models. And if I show you a model, you can kind of make some inferences about a molecule using that model. So go check out the very, very last video about formula mass. That's, besides the formula mass, the end of chapter 5. So go check out that formula mass video. Formula mass is extremely important. It tells us how much stuff there is in each individual molecule. So please go check that out, and I'll catch you later.